In this video, we'll look at a couple of reactions that can be classified as nucleophilic additions to carbonyl compounds. So this is an addition reaction, not a substitution reaction, and these types of reactions can happen with aldehydes and unhindered ketones. Aldehydes and ketones don't have a leaving group on them, and so it's not a substitution. We're not swapping one group out for another, we're adding a group. So first we'll look at cyanohydrin formation. So we'll use acetaldehyde. And this reaction uses a nucleophile that is the cyano group. So typically what you're going to see is a salt and then followed by acidic workup. And what we end up with is this guy. So cyanohydrin, here's our cyano group, and then the hydrogen comes from the OH. So this cyano group is going to be our nucleophile, and it'll be adding to the carbonyl carbon. If we just used HCN, this is a weak acid, so the equilibrium lies in that direction. So we can't really get H plus and CN minus. So we either need to use a salt, like what we did here, so that we have enough of the CN in solution to act as a nucleophile, or we need a strong base to deprotonate it, so that we can generate the nucleophile in solution. Just using HCN is not going to accomplish that because there's only a very small amount of the conjugate base, which is also our nucleophile. So if we go back and look at our mechanism here, we have this cyano group in the first step that's going to come in and it's going to add. So this has a negative charge, so it's going to be my nucleophile. And if we look at the carbonyl group, we've got a partial positive on the carbonyl carbon and a partial negative on the oxygen. So electron density is being pulled up and towards the oxygen. So let me see if I can find a different color here for the arrows. This nucleophile is going to come in and attack that carbonyl carbon, and those electrons are going to go up onto the oxygen as a lone pair. So here is our addition step, and then in the second step we add H plus, so it's a bad plus sign, oxygen can get protonated. Now we can't have the acid in there at the same time as our cyano nucleophile because it's a base. So it's a nucleophile, but it's also a base. So this is a 1,2. So first step, add the nucleophile. Second step, acidic workup. So that's like the last step, what we would do in the lab. Another addition type reaction, and I'll just use acetone this time, is the addition of water to make what is called a geminal diol. So geminal meaning on the same carbon. So these are in equilibrium with one another, and I have to do add water there, and this can be done under acidic or basic conditions, and we're going to look at the mechanism under both. So first we'll start under basic conditions. So remember, under basic conditions I should have species that are neutral or negative, but I'm not going to see anything that has a positive charge on it. So if I'm under basic conditions, I'm going to have hydroxide in there and H2O. Hydroxide is going to be more reactive than water because it has a negative charge. So this is going to be my nucleophile. A lone pair of electrons on that hydroxide is going to be attracted to the carbonyl carbon, add and kick those electrons up. So here I had an sp2 hybridized carbon, and now I have an sp3 hybridized carbon. Now the best acid that I have in solution is my water. So that gets me to my geminal diol. So in this case, I already have a good nucleophile because it has a negative charge on it. It's going to be attracted to that carbonyl carbon right away. It will add, and then I'll follow that up with my protonation step. Notice everything in here is either neutral or negatively charged. So we get the same product under acidic conditions. It's just going to go through a slightly different mechanism. So again, we'll take acetone, and this would be done in H2O and H+. And we'll see that the first step when we have acidic conditions is the activation of that carbonyl oxygen, so that it becomes positively charged, and it sort of activates that towards attack. So water is not a great nucleophile. It's not got a charge on it, so we're going to see this kind of activation step here, where we end up with oxygen with a positive charge, and of course that has a resonance structure where we've got a positive charge on the carbon. And now that this has been activated and there's a bigger partial positive on the carbon, or in the case of this resonance structure that I just drew, a full positive charge, the water nucleophile will come in and add. And now I'm just about at my geminal diol. I just have to do a deprotonation step. And so again, I'm in acidic conditions. The best base I have is water. It's going to come in, deprotonate, and that gives me my geminal diol. Now, this starting material again was sp2, and this guy is sp3. So I could use wedges and dashes to show the stereochemistry there. There is no actual chiral carbon because it has the same two OHs and the same two methyls coming off of it, but this would be in 3D. So if I looked at it, it's not planar. Those bond angles aren't 90, they're 109.5.